Okay, 8 a.m. and we can start, guys. So today we're going to introduce resistance. Actually, we already introduced in our recitation classes, right? But now we need to introduce it in the lecture. And also the method of an equivalent resistance, which can be used to analyze resistors. Okay, circuit with resistors, right? Okay, so let's start moving. So these are sections as usual. And all right, so in the previous class, we introduced what? Bunch of information about current, definition of current, direction of current, conservation of current, current density. Okay, basically everything which can be related to the current, electric current, right? And of course now, of course, all the current flows through a conductor, resistor, right? Or conductor with resistance, right? So the question is, how can we characterize that conductor, right? How can we characterize that conductor? And so in order to do it, we need to introduce well-known Ohm's law, right? Okay, so let's assume that we have a piece of a conductor, right? A nice cylindrical of some length L, right? And let's apply a potential difference. Connect a battery. So let's say delta V, right? Of course, as a result of this, current will start flowing. Electrons will start drifting, giving us electrical current, right? So in this case, the potential difference is the reason, right? And current is the consequence of that reason, right? So current appears because of the potential difference, right? Okay, and now let's start playing with these two quantities. Of course, obviously, if you increase potential difference, what will happen to the current? Current will also go up. If you increase potential difference more, current will increase more. And of course, if both quantities increases, of course, it's a natural desire to look at the ratio, right? Hoping for the best. And in this case, yes, it works. So if you look at the ratio of the potential difference versus current, within experimental error, all the time you're going to get exactly the same number. Of course, assuming that you're not doing anything to this piece of a conductor. You're not changing conditions, you're not changing temperature, nothing like this. So if you keep the system the same, the ratio of the potential difference versus current is going to be the same. If it stays the same, then it means that it's most likely it's some characteristic, intrinsic property of this conductor. Okay, if it's that, how it works, so let's give it a nice name: resistance. So resistance, by definition, that's how we introduce the resistance. It's a ratio of the potential difference across a conductor divided by current, which goes through that conductor. So by definition, and of course we all know this as Ohm's law, right? Actually, you know what? Ohm was not the first one who actually discovered this relationship, right? Cavendish did the first, found it first, but you know that even famous lab in England is named after him, right? But he was painfully shy, and for whatever reasons, whatever reason, he did not publish those results. And after his death, right, actually, people found in one of his drawers sort of information about that research. But since Ohm presented first, so it's named after him, right? Okay, so Ohm's law. And then, of course, what about units? Do we have to introduce the special SI unit for current? Oh, I mean, for the resistance. Definitely we have to, because resistance is used everywhere, right? Tons of people use resistance. And of course, in order to simplify their life, at least a little bit, instead of pronouncing all the time volts divided by amps, volts per amps, volt per amp, it's annoying, right? So ohms was introduced. So 1 ohm, and we used Greek capital omega, right? It's a 1 volt divided by amps, right? Okay, so a new unit. And now, of course, if you plot, for example, potential difference versus current, you will end up with this curve. You will end up with a straight line. And of course, the slope of that line is the resistance. It's called the IV curve, right? Actually, at some point, I remember I I had to characterize a bunch of quantum cascade lasers, and I was recording lots of IV curves. But of course, those IV curves looked much more sophisticated, much more complicated, much more informative, right? But for the just a simple resistor, it's just a straight line. So then, next one. Okay, you see, it's written Ohm's law. Is it a true law? You remember, like at the beginning of the semester, we spent lots of classes discussing this law, that law, right? And all the time I kept telling you guys, law, it means something fundamental, right? Timeless. You can apply that expression, okay, that law, at any point of the universe, at any moment of time, by anyone. You can apply it in US or in North Korea or in Madagascar, anywhere and everywhere it should work. Right? That's what we mean by a law. But in this case, is it a true law? And of course, you realize that it's not. Because look, even if I just use, for example, diet, and if I plot IV curve delta V versus I, it will have an exponential. Dependence. Or like in my case, my lasers, right? They have very complicated IV curve, which is far away from this expression. Even if you take the bulb, which is still effectively just a normal resistor, even bulb, because of lots of light it produces in temperature, it shows a more complicated dependence, relationship between delta V and I. So this Ohm's law, it only works for metals. So we actually, strictly speaking, we should say that it is just an experimental expression which happens to work for metals, right? So law in this case, it's not completely correct usage of the word law. But I guess it's just out of respect to the history, since when Ohm found it first, they believed that this is something universal, I guess, that this is a law. As a result, we keep calling it a law. But of course, in real life, it's not. It's not. Right. Yeah, and that's why I put this cartoon. Okay, so that's about Ohm's law. Enough. All right. Yeah. And so now you see, we have this conductor, right? And so now I can say that if you want to characterize this conductor with resistance, okay, it's a resistor, you have to know three parameters. You see, whatever is involved in this Ohm's law, R, I, delta V. Again, three parameters, like you remember with capacitor. If you want to characterize a capacitor, you need to know three parameters, C, Q, delta V. Now it's Ri delta V. Again, three parameters all the time. In a month, we will introduce inductor. And again, I will talk about three parameters, right? Okay, and now, so now we introduce Ohm's law, right? And so now makes sense to ask the question, what can R depend on? If we look inside of R, what we will be able to see there? Which quantities can be involved in to define R? Okay, we assume that we have some piece of resistor, like I know, cylindrical shape, right, and so on, of certain length, right? So what can be involved to find R, right? Okay, so let's assume that we have this piece of a conductor, which of course is going to have some amount of resistance, right? So you see length L, cross-sectional area A, right? Cylindrical shape, right? And what I'm going to sort of discuss now, it's not a proof. No, it's far from being a proof. Of course, book, I think, shows the proof of the expression which I want to write. This is sort of like a conceptual analysis. So, first question. I have these two pieces of conductors, and of course, they will have some amount of resistance. What you see, one is long, the other one is much shorter. These are just posts from optical labs, right? All right, so they have the same cross-sectional area. they made of the same steel, the same material, right? And of course the question, which one is going to have larger resistance? And of course you all understand, right? And usually during the normal semesters, everyone tells me immediately, of course, the longer one is going to have larger resistance. And that's absolutely correct, right? So just a short justification why that is true. Because what is nature of resistance? What lies behind resistance? If you dive inside of the conductor to see. And the reason is because electrons, which give us current, they're not flying through an empty space, right? They're flying through a piece of metal, right? Which has a crystalline structure, which is basically a bunch of positively charged atoms. Of course, why positively charged? Because they give lots of electrons, giving us tons of free electrons in the conductor, right? So, of course, in this crystalline structure, we have positively charged ions, something like this. You see, bunch of positively charged ions, right? And of course, electron is going to fly through this mass, right? And of course, electrons, they fly along a straight line, because whenever they start feeling electric force, which comes from the either potential difference or electric field, of course, they're going to fly along a straight line. And of course, sooner or later, they're going to collide with the first atom, right? Collision, right? Collision, then concussion, recovery, right? And then again, that electron will be accelerated by the electric field, and again it will fly for some short distance, and again collision with the next atom. It's like if you try to run through the forest along a straight line. Of course, within a few meters you're going to meet the first tree, right? After recovery, again, if you start running along a straight line, again in a few meters you're going to collide with the second tree. Of course, you're going to make a progress, you're going to move forward, but with lots of collision and concussion, right? So that's what lies behind resistance, all these collisions. Of course, this process is quite complicated. But in physics, we just introduce resistance, and we're trying to describe all this complicated process with just one simple parameter, quantity resistance, right? And of course, the longer the conductor, the larger number of collisions you're going to, electron is going to experience, right? And of course, the larger resistance is going to be. So it means that the length of the resistor must be in a numerator of the expression for the resistance. So I can write down that R is proportional to L. Again, it's not a proof. You can say, why it's not, for example, second power of L, or maybe square root of L. No, it's not a proof. We're just trying to justify. Of course, it can be proved just looking what happens inside of the conductor. Again, in the books, it's done in the books. If you want, you can read that, right? I just don't want to spend time discussing that, right? Okay, so that's the first. It should depend on the length of the resistor or conductor, right, with resistance. Now, the second part. What if I have these two conductors, which of course going to have some amount of resistance? You see, they of the same length, but this one has large cross-sectional area, okay, reasonably large, and this one has small cross-sectional area. So the same question, which conductor or which resistor out of these two is going to have larger resistance or smaller resistance, right? And here usually students start hesitating, start doubting themselves, and quite often giving me actually the wrong answer. Let's again justify in order to come up with the correct conclusion. And I usually give this analogy from our everyday life. Right? Imagine yourself, rush hour at around 8:30 a.m. Okay, during normal life, right? Downtown crossing in Boston subway station, right? All right, platform filled with people, right? And let's say train comes to the station, right? So a small door, okay, reasonably small door gets open, right? And then what happens? All these people start squeezing, right, into the train, right, into the car. pushing each other, elbowing, right? Coffee being spilled, right? So they managed to get in, but with significant amount of resistance, right? And here there is a small photograph from, I think it's a Tokyo, right? It's famous, right? For lots of people use a subway, right? Okay, so here you see we have a reasonably small cross-sectional area of the door. As a result, we have, okay, they have lots of resistance, right? But now let's imagine a fairy tale situation. Train comes, yeah, to the station, and the whole front wall of the train gets lifted. What would happen in this case? All these people in the platform, right, they would be able to just step in without significant amount of resistance. Now, you see, we increase the cross-sectional area, and now resistance goes down or went down, right? So now using these arguments, I claim that cross-section, and the same happens with these electrons. I claim that the cross-sectional area must be in the denominator downstairs of the expression for R. As a result, I can write that R is proportional to 1 over A, where A is the cross-sectional area. Okay, and now, so now we introduce two quantities. Now the last one. Let's imagine that I have two resistors. One is made of steel like this, but a second one made of gold. Of course, I don't have that amount of gold, right? Okay, I can actually open, right? So, all right. So we have, oh, aluminum and gold, right? And if I ask you the same question, which piece of these resistors are going to have larger resistance? Okay, actually, we cannot say we cannot say immediately which one is going to have smaller resistance, but we can say for sure that definitely they should have different resistance. Right, Gut's feeling should tell us that different material should have different amount of resistance, right? So, and there must be a quantity or parameter involved in this expression which would describe the material only. So that, for example, gold, it's at this parameter, aluminum, it's at this parameter, copper, it's at that parameter. And of course, how you introduce this parameter in the numerator or denominator, it's actually at this point, it's up to you, right? Most of people who works in electronics, of course, they introduce what is called resistivity, and it goes in the numerator, right? So resistivity, rho, it's basically a quantity describe a material. And usually it's measured experimentally, and there are thick books where you can open, okay, so gold, it's this number, copper, this number, okay, alloy of this with that material and percentages are given, it's this resistivity, right? So you can open up the book and find the number, or maybe measure it experimentally by yourself, right? So one way of introducing material into the expression is to introduce resistivity. And resistivity goes in the numerator, right? In a couple of minutes, I will also show you that, for example, if you work in the world of photonics, right, with semiconductor materials, those people usually prefer to introduce a different parameter, and that parameter goes in the denominator, and it's called conductivity, right? For them, it's slightly more convenient to work with conductivity. It depends on where you do your research. Sometimes resistivity is better, sometimes conductivity is slightly better. It's not a big deal, but slightly is enough to make a decision to use this or that quantity. Right, okay, so now finally, I can write the whole expression. So R equals resistance equals resistivity times length of the resistor and divided by the cross-sectional area. All right. Okay, so first of all, what's the major feature of this expression? Major feature is it does not depend on the electric field, does not depend on the potential difference, neither charge, none of the electric quantities. It depends only rho, material, describes the material, L, geometry, A, geometry. It depends basically only on the geometry and the material used to fabricate this or that resistor, right? Very similar we've seen when we introduce inductance, or not inductance, capacitance of a parallel plate capacitor. right? You remember several classes ago, we introduced something like this, right? C equals epsilon naught A divided by D. Again, epsilon naught, it's a material, vacuum, right? And then A and D are geometry, right? Even you see, even kind of, there are some similarities in structure. That's why a resistor, if you buy it, it's labeled, because it depends only on the material and geometry. And if you build it, you can calculate it and label this or that resistor, right? As I said several times already, there are lots of similarities between these three elements: capacitor, resistor, and then in a month we will introduce an inductor. Lots of similarities. Okay, so now, yeah, and of course, as I said, there are no any special units of resistivity, just ohms times meters, right? And of course, as I said, if sometimes people prefer to use conductivity instead of resistivity, right? And they're of course connected through, okay, connected as 1 over. So conductivity equals 1 over resistivity. Whew. Okay, so now next, I want to emphasize, because first, for some of you, it can be confusing at the very beginning, right? They sound kind of similar: resistance, resistivity, but of course they're quite different. What's the major difference? Again, resistance, it's a quantity which describes a particular object, a particular resistor, which is made of a certain material, which has some length, some cross-sectional area. So it's a quantity describing an object, a resistor. Resistivity describes material: gold, copper, aluminum, tungsten, molybdenum, right? Whatever material is used to fabricate a resistor. So resistance, it's a property of an object, of a resistor. Resistivity, it's a property of a material. And since you're going to use resistivity to do your homework, do not use Google. Google might give you slightly different number, but of course, Mastering Physics is programmed to use numbers given in the book. So use table 27.2. So I just copied and paste that table, right? And you see we have a bunch of materials. I mean, bunch of metals, bunch of metals, right? Then here's the column for resistivity and the column for conductivity, right? And of course, if you take a reciprocal, you can get a resistivity from conductivity and conductivity from resistivity. Right, and that's what I just told you, right? So that characterizes material, and this characterizes resistor and object. Whew. Okay, so now what's next? Question for you, right? And as usual, the poll, and again, it's a conceptual question number 1. I think I posted 3, so it's number 1. All right, just scroll it up slightly. All right. So what do we have here? We have a piece of circuit, you see, with a resistor. Actually, this is the symbol used to show the presence of the resistor in the circuit. All right, in Europe, they just use a small rectangle. For me, sort of drawing small rectangle is easier. Every time when I try to draw something like this, it looks very, very ugly, right? All right, okay, so, and you see there is a current, and we know the direction of current. Current flows that way. And the question is, which point is at higher potential? A point A or point B? Which point is at higher electric potential? Very important, reasonably simple, but very important, because when we get to Kirchhoff rules, we're going to use this often. Okay, anyway, so give it a try, and yeah, I'll give you maybe like 30 seconds. It should be enough, right? Because in this case, you don't need to do any calculations. I just want you to think about this. Okay, I see your answers. And sorry for all these symbols are capitalized, because when I copy and paste, all the subscripts appeared as normal big symbols, right? And when I create a poll in Microsoft Teams. Okay, nice distribution. Some people believe that potential is the same, but then how come that current is flowing? If potential is the same, then the current will never be able to flow, right? Electrons will, okay, so now that option is going down. Right? Now, okay, now everyone change her mind. Okay. Okay, it should be enough, right? Of time for you to think. And so, discussion is quite simple. Okay, you remember in the previous class we introduced direction of current. And by convention, direction of current, it's a direction of motion of positive charges. As a result, current flows from plus to minus, from the positive electrode of the battery to the negative electrode of the battery, right through the circuit. And of course, we all know from the days when we were discussing electric potential that any positively charged object has higher electric potential than any negatively charged object, because here potential is positive, here potential is negative, right? So obviously positively charged object has higher electric potential. And since current flows from plus to minus, it means that current flows all the time from the areas with higher electric potential to the areas with lower electric potential. So whenever you see direction of current, you should be able to tell immediately that points over here is at higher potential than points over there, because again, current flows from plus to minus, from points with higher electric potential to the points with lower electric potential. So remember that current all the time from plus to minus, right? Okay, so in this case, VA, of course, potential at point A is larger than potential at point B. Okay, I put plus and minus. It just means that here electric potential higher, there electric potential is lower. That's what it means, plus minus, right? Okay, so, and most of you answered it right. Okay, good, thanks. Right, and now, it's a very simple, but it needs to be pronounced. It needs to be, we have to emphasize on that, because sometimes this simple connection between the current direction and the electric potential is missing, right? So the next question, all right, also not complicated, but again, we need to again emphasize on this. We have this piece of a conductor with, of course, with resistance, right? And let's assume current flows through this structure. And the question is, so you see we have the first component and then the second component of this conductor with resistance, right? So what about current? Current in the first component and current in the second component. And you see I1 is larger than I2. I1 is what? Equal I2. I1 is less than I2, and there is not enough information to compare these currents. So first, just compare currents in the first component, or first part, in the first part of this conductor, and the second part. Actually, in the question, it's called segment. Okay. And so now the conceptual question, conceptual test 2, right, you see. And I see you already started answering. Okay, nice, nice. Again, this question doesn't require any calculations. Pretty much, I'll give you 30 seconds. It should be enough. Plus, we discussed this in the previous class. I just wanted to some things must be mentioned several times, right, in order to get that into our heads, right? Repetition is important. Okay, great. It should be enough, right? Now discuss, but actually there's nothing to discuss. It's basically, you remember from the previous class, conservation of current, when there is no any junction point in the piece of a circuit, right? There's no junction point. So current must be exactly the same, right? So if you have conductor like this, you remember I told you it doesn't matter where you measure your current, current must be the same. Or if you have a wire or conductor with different cross-sectional area, with varying cross-sectional area. Again, it doesn't matter where you measure current, here, here, and there, or there, current will be the same. And I give you analogy with water flowing through pipes of different or varying cross-sectional area, right? Just water in some parts will flow faster, giving us, let's say, 5 liters per second. But in the parts which have a larger cross-sectional area, water will flow slower. But because of the larger cross-sectional area, the amount of water per unit time will be the same. Like let's say 5 liters per second, right? So the same true for current. It doesn't matter what's the cross-sectional area, current will be the same. But now, what about so for the answer for this one is, of course, current is the same, and most of you answer it right. Good. But what about current density? Okay, current density depends on the cross-sectional area. You remember definition of current density? You need to take current and divide it by the cross-sectional area, right? So since area is involved, it means and plus it is in the denominator, it means that smaller cross-sectional area, okay, part A, right, this segment one, part 1, of course, is going to have larger current density. And of course, part 2, this section 2, is going to have smaller current density, although current the same. Right? Okay, so just wanted to remind you about this, because a few times I give questions on the exam like this, not very often, but I think a couple of times. And usually part 1 is good, but part 2 about current density, and a few students missed that part. Missed the complete understanding. Okay, so now next. Actually, we started using already some elements. Let me just summarize quickly, right? I just copied it from the book. Of course, battery we represent like this in the circuits. Of course, I'm lazy to draw all these bars, right? I just use only 2. Longer one represent the positive electrode, the shorter one, negative electrode. A wire, it doesn't matter if it's twisted or bent. Every time we try to draw a straight line, just it looks better, looks more elegant, right? Then resistor, again, as I said, in Europe, this symbol is used. I mean, here, this symbol is used in Europe, just a rectangle, right? Then a bulb, okay, it's complicated. Whenever I have to draw bulb, I usually draw something even fancier than that, right? But anyway, that's the symbol of the bulb, right? So then junction point, right? You see? Then capacitor we already used many times. And then in a couple of classes we will use a switch. We'll start using switch when we get to RC circuits, right? So, and of course switch is represented like this, right? Using that symbol. They're more or less self-explanatory, so not a big deal. Okay, so now at this point we can say now we know how we can analyze a single resistor. Again, as I keep saying, 3 parameters. Ri delta V, resistance, current, potential difference. But what if we have more than one resistor? What if we have 2, 3, 5 resistors? All right, how can we analyze them? And again, what does it mean analyzing them? It means that for each of those resistors, we need to know Ri delta V. So if you have 3 resistors, you need to know 9 parameters. 4 resistors, 12 parameters, and so on. So now we're going to restrict ourselves to the cases where resistors are connected either in series or in parallel. It's a significant limitations, right? Because there are plenty of situations where resistors are not connected neither in series nor in parallel, are connected neither in series nor in parallel, right? Okay, so now I'm planning to derive formulas similar to the ones which we derived for capacitors, right? Although we've done it in our recitation classes, right? Here about resistors, we're going to do it in the lecture using view graphs. I posted my, if you okay, I posted my pre-lecture slides and you can see, right? So you don't have to try to follow me because right now I'm going to move a little bit fast and it will be difficult for you to write after me. Okay, so let's start with a case when resistors connected in parallel. And let's start with the real circuit. And you see there are 3 resistors. And I claim that they're connected in parallel and they're connected to the battery plus minus, right? And again, the idea behind the equivalent resistance is very similar to the idea behind the method of an equivalent capacitance. You need to replace all these 3 resistors with a single resistor, which we call an equivalent resistor, right? Like this. So this is the real circuit. This is an equivalent circuit. And you see, instead of those 3 resistors, I introduced R equivalent. And when you do this replacement, I have to pronounce the same magic words. When you replace those resistors with an equivalent resistor, the rest of the circuit must work in exactly the same way. In this case, the rest of the circuit is just a battery. But of course, in real life, it can be a very, very complicated circuit where you can spend, I don't know, maybe weeks building that. And if you do this replacement, you don't want to destroy the work of the rest of your circuit. All right. So if delta V, if battery in this circuit provides potential difference delta V, exactly the same delta V must be there. If current I, let's say 5 amps, is taken from the battery in the real circuit, exactly the same current must be taken from the battery in the equivalent circuit. Right, you see exactly, okay, exactly the same words are pronounced like, okay, not exactly, similar words, right? Like when we were analyzing capacitors connected in series and in parallel, right? Okay, and so now again, we want to analyze resistors. Again, 3 parameters, R, I, delta V. Right? Our final goal, actually, we need to get the formula which can be used to calculate R equivalent, right? So R will be at the very end. So it means that we need to analyze 2 parameters, I and delta V, current and the potential difference. And I usually start, what can you say about potential difference of all these 3? Probably I should open this first, about the fact that when you replace, the rest of the circuit must work in exactly the same way. All right, so back to delta V. So what can you say about the potential difference across these 3 resistors? I think everyone sees that potential difference must be the same. Actually, that's the major feature of things connected in parallel. If potential differences are the same, it doesn't matter what you attach over here, which battery, and if potential difference exactly the same, so that's the sort of like a test that you have to run to convince yourself that in the elements are connected in parallel, potential differences must be the same, right? These you can use here bulbs, motors, whatever connect. And of course, if potential differences between these elements are exactly the same all the time, it means those elements are connected in parallel, right? So now I can write the delta V1 equals to delta V2 equals to delta V3 and equals to the potential difference across the battery. Now I want to add to this line of equal things information about the equivalent resistor. And it's very simple because delta V1 equals delta V2 equals delta V3 equals to this delta V. But again, you remember the rest of the circuit must work in exactly the same way. So it means that exactly the same delta V must be here. And this delta V is applied directly across that equivalent resistor. So potential difference across an equivalent resistor is also delta V. So I can add to this line of the delta V's delta V across an equivalent resistor. So this is an important piece of physics which we are going to use analyzing resistors connected in series and in parallel. So potential difference across an equivalent resistor equals to the potential difference across resistors connected in parallel. We need to remember that, right? So this is an important piece of information which we need to remember from this slide. Okay, and now we need to get a formula for the resistor. R equivalent. And so now what's left? Which parameter left to analyze? Current, right? R will be at the end. We discussed delta V, now current. And let's assume that current I is taken from the battery I. And of course, where does this current go? Of course, it will get split, and some of that will go through the first resistor, I1, through the second resistor, I2, and some current, of course, will go through the third resistor. Now we can use conservation of current in the presence of a junction point. In this case, actually, we can see 3 junction points, right? So obviously, all right, current I must be equal to I1 plus I2 plus I3, conservation of current. Okay, so great. Now we're getting an expression which can be all right, which can be used to get the formula for the equivalent resistance. But we just need to replace these currents with what? Resistances, right? So we need to introduce into this formula, not formula, the equation. We need to introduce in this equation resistances. How that can be done? Ohm's law, we have for that Ohm's law connecting all these 3 parameters, right? So Ohm's law, using Ohm's law, we can write that I1 will be equal to delta V divided by R1. And you see I dropped the subscript next to delta V, right? Because all delta V's are the same. All delta V's are the same, right? So delta V over R1, then I2 will be delta V over R2, and I ran out of space for I3. So that's what I'm going to introduce in the right-hand side of the equation. And now we need to write down the total current. But the total current we need to get from an equivalent circuit so that we can bring into the game R equivalent. You see, steps are very similar to the steps which we have done discussing capacitors. Even the structure of the slides I'm trying to keep the same. So again, using Ohm's law for the equivalent circuit, we can write that current, which is over here current, the same as over there, right? You remember the rest of the circuit must work in exactly the same way. So current I here, current I there. So we can write that current I equals delta V, which is applied across the resistor divided by R equivalent. And that current goes into our expression. We're almost done. So now let's just rewrite it in terms of delta V divided by R's. Since delta V's are the same, we can cancel that. And we're getting the formula which we need to calculate the value of an equivalent resistance. So from this slide, we need to remember, of course, this important piece of physics about the potential differences across an equivalent resistor and the resistors connected in parallel. And we need to remember this formula. Again, based on my experience, students have no troubles applying these formulas, but have lots of troubles applying these. Okay, so now the next resistors connected in series. Again, structure of the slides will be very, very similar, right? Very, very similar steps. On purpose, I'm trying to keep them the same. It will be easier to remember. Okay, so real circuit, resistors connected in series now. All right, and again, we need to introduce an equivalent circuit, and we replace these 3 resistors with a single equivalent resistor. So and again, the rest of the circuit must work in exactly the same way, right? So it means that if delta V, if this battery provides delta V, exactly the same delta V must be in our equivalent circuit, right? And of course, if current I is taking from the battery in the real circuit, exactly the same current must be taking from the equivalent circuit, from the battery in the equivalent circuit, right? And again, 3 parameters we need to analyze: R, I, delta V, because we're still dealing with resistors. Again, R will be at the end because that's what we want to get. We want to get the formula for the equivalent resistance. So we have 2 parameters left, I and delta V. And now let's start with current, right? For obvious reason. So what can you say about the current through the first resistor, second and third resistor? they must be the same because it's a conservation of current because we don't have any junction points over here. We have a single loop, right? All these resistors connected in series, right? So current is the same. Pretty much that's the major feature of things connected in series. Okay, in this case, resistors connected in series. Current is the same under any conditions. It doesn't matter how you connect that in the circuit, right? If you keep the same structure, right? If the current is the same, so it means that resistors connected in series, right? Okay, so current is the same. So where is it here? I1 equals to I2 equals I3 and equals to the current taking from the battery. Now again, we want to connect to this line information or bring to this line information about current through the equivalent resistor. And connection is very simple because again, the rest of the circuit works in exactly the same way. So it means that this current I is equal to this current. And of course, in this equivalent circuit, this current I flows through equivalent resistor, right? So I can add to this line that it also equals to I current, which goes through the equivalent resistor. So this piece of physics, again, important piece of physics, which we will need to analyze circuits full of resistors connected in series and in parallel. So in this case, current through the equivalent resistor equals to current, which goes through resistors connected in series. Okay, and now we need to get the formula for R equivalent. So again, and we have on the last parameter left, delta V to analyze, right? R at the end, I we just discussed, and now what's left, delta V. What can we say about delta V? The total potential difference across the circuit, which is provided by the battery, delta V, right, must be equal to delta V1 plus delta V2 and plus potential difference across the third resistor. So delta V equals delta V1 plus delta V2 plus delta V3. And again, we need to introduce resistances into this equation. How? Again, using Ohm's law like in the previous slide. But of course, now we will have to write Ohm's law in a slightly different way, right? So in terms of delta V equals Ri, right? So R1 I, and again, you see there are no subscripts next to I because all those currents are the same, right? And for delta V3, R3 times I. So that's what we're going to introduce into the right-hand side of the equation. But left-hand side, total delta V, again, we will get from the equivalent circuit, right? Delta V across the battery and delta V across the resistor, it's the same, right? So delta V across the resistor, it will be current I times R equivalent. So from the equivalent circuit, we can get, okay, where it is? Here it is. All right, delta V equals R equivalent times I, and that's what we're going to introduce to the left-hand side of the equation. And almost done. So now we can rewrite it in terms of I's. This I is the same, current is the same, so we can cancel that. And we're getting the formula. The nicest possible formula. In order to find an equivalent resistance, you need to just add values of those resistors connected in series, right? So from this slide, we just need to remember, of course, this important piece of physics and the formula which can be used to find an equivalent resistance. Again, students, based on my experience, again, have no troubles with this, but plenty of troubles with that. Okay, so after this, we have only 1.5 minutes left. All right. After this, I was planning to look at the example, all right, to analyze circuit with 3 resistors, some of them connected in series, some of them connected in parallel, right? But we're running out of time, right? So we're going to do it in our recitation classes, right? Your recitation instructors are going to do it. And that analysis is very similar to the analysis we've done to analysis of circuit full of capacitors, right? You remember in our recitation classes, capacitors connected in series or in parallel. But still, since we have 1 minute, let's answer this clicker question, the last one, number 3. It's partially related to physics, right? Partially related to physics. So, of course, car, right, has two headlights, two bulbs. How should they be connected or wired? In series or in parallel? Again, it's partially, of course, real wiring is more complicated, but everything is oversimplified, right? So, how should wires be, bulbs, how should bulbs be connected or be wired? Right. Okay, I will hold you for one extra minute, right, or half a minute. It's sort of more like for fun. Again, guys, I posted my solutions for some of you who came later. My solutions to the exam. You can find it in the Blackboard in the folder exams from the past. All right, and if you disagree about our grading, all right, you can go to the grade scope and fill out the regrading form. Right, it's very simple. Or come to office hours, my office hours, or your recitation instructor to discuss. If you're not confident, if you're kind of afraid to challenge grading, you can discuss whether it's worth of challenging the grade, right? Score. Right? Don't be afraid. I already changed one grade. Yeah, I already changed one. Okay, all right. Let me look at your results. Oh, okay, awesome, right. Okay, I see that you already answered quickly. Let's discuss, let's assume that somebody wired bulbs like this, using this situation, if they're connected in series, okay. And let's imagine that one bulb is, I don't know, gets burned out. It means that since we have here only one loop, if one bulb gets burned out, then it means that this circuit is going to be open and current is not going to flow even through the second bulb. So pretty much you will end up in that case in a complete darkness driving on the road, right? So of course, from the safety point of view, it's a no case, right? Completely no, right? But what about these situations when bulbs are connected in parallel? So if one, in case of troubles, if one gets burned out, right? So let's say this one, the lower one, right? So, but here we have two loops. So if this is out, then of course the current will stop flowing through this smaller loop. But still current can flow through the larger loop. And of course current will get larger. So we assume that the bulb is strong enough to handle that current, right? So this bulb is out, but this bulb will be still working and actually giving us even more light. So in this case, so you can still safely drive, right, with one bulb instead of two, right? All right. So of course, parallel case is the right case, right, to use, because in this case, in case of troubles, you will still be able to see something in front of you, but in this case you will end up in complete darkness. Okay, so that's why I told you it's partially related to physics, because it's about physics and safety, right? Just a fun question.